Hey everybody, this is Mr. Misuro, and today I want to take a step away from what we've been talking about with oceanography, the idea of subduction and trenches and plate tectonics and what's happening with all these tectonic plates and how the oceans are moving. And I want to actually start exploring another area of oceanography, how water moves in the ocean. And I want to start by talking about currents and upwelling and downwelling. Hopefully, I want you to get not only what currents and upwelling and downwelling are, but also why they're important in the ocean, what they're actually doing in the ocean or for the ocean. So, we'll do currents first. Currents is this horizontal swirling of water on Earth's surface. Currents swirl clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. And this clockwise and counterclockwise, this opposite turn, is actually caused by what's known as the Coriolis effect. I'm not going to go too much into what that is. It has to do with how the oceans are on a rotating Earth and how wind and movement is actually felt on a rotating surface. But what I need you to understand, or what's interesting, is that this is the reason why hurricanes, for instance, swirl one way in the northern hemisphere and another way in the southern hemisphere. This is the reason why tornadoes swirl one way in the northern hemisphere and another way in the southern hemisphere. This is the reason why even toilets go one way in the northern hemisphere and another way in the southern hemisphere. And before I go on, I should point out that that's actually not the reason why those toilets go the opposite way. Toilets don't go the opposite way in the southern hemisphere. The Coriolis effect, this opposite swirling, is actually a much bigger phenomenon. It doesn't happen on the scale of toilet bowls and sinks. It happens on the scale of entire oceans. But if we had a toilet the size of the ocean, it would turn clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. So, what causes this swirling of ocean water? The answer is wind. Wind blows on water, and when wind blows on water, it causes water to swirl one way in the northern hemisphere and one way in the southern hemisphere. But why do we care about this? We care about this because currents help warm water get circulated to the poles, and then they help cold water get circulated back to the equator. In other words, currents help warm up polar waters and cool down equatorial waters. If it wasn't for currents making sure that the poles aren't too cold and that the equators aren't too hot, there wouldn't be able to be life throughout the surface of the ocean. There would only be life in this very narrow yellow band in the ocean. There's life all over the ocean. We know this. And the reason is because currents are helping regulate the ocean's temperature, making sure that the equator isn't too hot or that the poles aren't too cold. But what about upwelling and downwelling? Upwelling and downwelling has to do with density. Water sinking or downwelling in itself is caused by temperature and salinity. Cold, salty water sinks. And that opposite, warm, relatively fresh water, rises. In other words, cold, salty water downwells to the bottom of the ocean, and warm, relatively fresh water upwells to the surface of the ocean. But why do we care about this? We care about it because upwelling and downwelling circulate oxygen to the bottom of the ocean and nutrients to the surface of the ocean. In other words, the bottom of the ocean isn't near any air. It has no light for photosynthesis. The only reason there can be organisms on the bottom of the ocean is downwelling takes oxygen from the surface layer, from the very, very top of the ocean, and puts it down there so those organisms on the bottom of the ocean can breathe. But how do we get nutrients from the bottom going to the top? Well, in order to tell you this, I have to describe to you what I like to call the two Chinese food buffet scenario. We're going to go to two Chinese food buffets. Imagine two Chinese food buffets. One is a really, really, really crowded buffet, right? You have to stand on line to get to every steamer tray, and you're basically pushing people out of the way to get everything. Super crowded, a lot of people eating there. My question is, are you going to be able to eat your General Tso's at that buffet? Well, no. It's probably going to be taken up by everyone else at the buffet. Versus a not crowded Chinese food buffet. Now, if you're the only one in there, there's going to be plenty of General Tso's there, plenty of food. Well, the bottom of the ocean is like the empty Chinese food buffet, and the top of the ocean is like the crowded Chinese food buffet. The more organisms in any location, the less food that's available to any single one of them. Just like there was less food available to you in the crowded Chinese food buffet, there's less food available to organisms at the top of the ocean because there's more organisms there. Just like there is more food, it was easier to get food in the bottom of the ocean, means that there's going to be, like the empty Chinese food buffet, more nutrients, more food at the bottom of the ocean. More organisms, less food, top of the ocean. Less organisms, more food, bottom of the ocean. And it's upwelling that allows those nutrients to be sucked up from the bottom of the ocean to the top. And necessarily, it's upwelling that allows there to be such an amazing amount of organisms at the top of the ocean. Without upwelling bringing up food for all of them, there wouldn't be able to actually have that many organisms at the top of the ocean. Upwelling and downwelling, caused by density differences, temperature and salinity. Cold, salty water is more dense and sinks. Warm, fresh water is less dense and rises. Why do we care about that? Because that sinking brings oxygen down to the depths, and that rising brings nutrients up towards the surface. For our region, for the northern hemisphere, upwelling and downwelling takes place when in the winter. Why? Because that's when the surface layer of the ocean and the bottom of the layer of the ocean are going to be similar temperatures. In the winter, the surface layer is cold and the bottom layer is cold. And so because they're similar temperatures, there's going to be similar densities. And that's when the temperature is the same. There's going to be the most easy mixing between the surface and the bottom layer. For us, that's January, February, our winter. For the southern hemisphere, that would be our summer. If you take upwelling and downwelling and combine them with currents, what you get is this thing called the Great Ocean Conveyor. If you combine upwelling and downwelling and currents, what you can actually do is you can trace how molecules of water circulate throughout the ocean. If you were a single molecule of water, you can ride all the upwelling and downwelling events, and you could ride all the currents, and it would take you about 4,000 years to circulate throughout the entire ocean. In other words, the water that's on the Jersey Shore now, the last time that water was there was the very beginning of the ancient Egyptian empire, before the pyramids were even built. So the last time that water was visiting New Jersey, Egypt was just kind of coming into vogue. So today, I wanted you to understand what causes currents, that's wind, and why they're important. The idea that currents help regulate ocean temperature, circulating warm water to the poles and circulating cold water to the equator. And I also wanted you to understand what drives upwelling and downwelling, that's temperature and salinity differences, density differences, and why they're important, specifically downwelling bringing oxygen down to the depths and upwelling bringing nutrients up to the surface. Thanks very much for listening, and stay tuned for the next lesson where I'll start talking about waves and specifically breaking waves.